theorem, let T be a mapping from U to V and S is a mapping from V to W, be two linear maps, then if S and T are non-singular, then ST is non-singular and ST inverse is equal to T inverse S inverse. Second one, if ST is 1 1, then T is 1 1. Third one, if ST is onto, then S is onto. If ST is non-singular, then T is 1 1 and S is onto. If U, V and W are of the same finite dimension and ST is non-singular, then both S and T are non-singular. So we have to prove these 5 parts for this theorem. So let us start with its first part. Initially, let T is a mapping from U to V and S is mapping from V to W, be two linear map. Now for the first part, see here it is given that if S and T are non-singular. So since S is non-singular, so what we can conclude from non-singular? We know that if any mapping is non-singular, then it is 1 1 onto and linear. And we also know one more thing, if any mapping is non-singular, then it has its inverse. So from here we can conclude this, if S is a non-singular, then S inverse is defined. If any mapping is non-singular, then its inverse is defined. So if its inverse is defined, since S is a mapping from V to W and S inverse is defined, then S, composition of S and S inverse is IW and S inverse S is IV. We know how we can write this. Again, since T is non-singular, then T inverse is also defined, and if it is defined, then composition of T inverse is IV and T inverse T is IU. Now we have to prove this part. So let us start. ST T inverse S inverse is equal to, see, since these are all linear map, so we can write S T T inverse S inverse, and from this we can write S T T inverse S inverse, and from this we can write S, and T, product of T and T inverse is nothing but IU S inverse. With T and T inverse is IV S inverse, this is nothing but S inverse, and this is nothing but IW. Similarly, now T inverse S inverse into ST is equal to T inverse S inverse ST, and this can be written as T inverse S inverse ST, and we have already value of S inverse S. This is I. S inverse S is IV T. So this is equal to T inverse T, which is nothing but IU. So we have T inverse S inverse into ST is equal to IU, and ST into T inverse S inverse is equal to IW. So from here we can conclude that ST inverse is equal to T inverse S inverse. Hence, ST is non-singular and ST inverse is nothing but T inverse S inverse. Now for second one, it is given that if ST is 1 1, then we have to prove that T is also 1 1. So let us start its proof. Now to prove that T is 1 1, T is 1 1. Here you can easily remember that here ST is not defined. Not defined means how ST is mapping, actually it is not given. So in this case I have already told you, and so this type of question we will use concept of nullity, that kernel T contain only 0 element. So that concept we will use here. So let U be any element of nullity T. Be arbitrary. If U belong to nullity of T, then T of U is obviously theta V, or we can say 0 element. Now taking composition of S both this side, so this become S of theta V, and S of theta V is nothing but theta W. Here this we can write, since S is linear, therefore S of theta V is equal to theta W. Also we can write this as S of product of ST of U is equal to theta W. This implies that this U belong to nullity of ST, and which contains element theta U, since our ST is 1 1. See, n of ST, nullity of ST is equal to theta V, we can write, since our ST is 1 1, because we have theorem, if any mapping T is 1 1, then its nullity contain only 0 element, if and only with if and if only condition. So if this happen when ST is 1 1, so obviously n of ST is equal to theta U. Now this implies that U is equal to theta U, that is nullity of T contains, or we can say that U belongs to nullity of T implies U is equal to theta V. This implies nullity of T contain, theta U. This implies that T is 1 1. Here if ST is 1 1, then nullity of ST contain theta U. If T is 1 1, then nullity of T contain theta U. So our next part is C1. If ST is on 2, then S is on 2. For this, let ST be on 2. Then we have to prove that S is also on 2. Now we have S is a mapping from V to W. T is a mapping from U to V. Then obviously ST is a mapping from U to W. Now since ST is on 2, for every W belongs to W, there exists, here our ST is on 2, therefore for every W belongs to W, there exists a vector u belongs to u such that st of u is equal to w. Again, I can write this as s of t of u is equal to w. Again, we have t is a mapping from u to v and t of u belongs to v. Therefore, for every w belongs to w, there exists a vector v belongs to v such that, or we can write this v is nothing but t of u, such that from here we can write this s of v. I am writing v in the place of t of u, so s of v is equal to w. So this imply here my st were onto, but from this condition we can conclude that our s is onto. For next part, our d1, if st is non-singular, then t is 1 1 and s is onto. So it is given in the question that st is non-singular. That means our st is linear, st is 1 1 and st is onto. But we have to prove that our t is 1 1 and s is onto. So let us start. Say st is non-singular. What we can conclude from this? This implies that st is 1 1 and onto. But see, we have a past 3 part that, see, our part B says that if st is from B part, if st is 1 1, then t is 1 1. We have proved it already. So this is proof. St is 1 1, then t is 1 1. From C, if st is onto, then s is onto. This thing we have proved already, so we are writing this directly here. So our fourth part is done. Now for the last one. Now for last part, E. For D1, it is given that if U, V and W are of the same finite dimensional, U, V and W are of the same finite dimension, here it is important to remember that U, V and W are of same finite dimension and st is non-singular. Then we have to prove that S and T are non-singular. So see, here it is given that U, V and W are of same finite dimension. That means dimension of U is equal to dimension of V is equal to dimension of W. So from this what we can conclude? we can conclude that if T is 1 1, then obviously T is on 2, because dimension of U and V is equal. That is, suppose here it is U and this is my vector space V. This is mapping T. If T is 1 1, that means every element of U is related to V. But T dimension of both is equal, then obviously every element of V has its pre-image. Similarly for S, if S is 1 1, then obviously S is on 2, and if S is on 2, then obviously will be 1 1. So from this what we can conclude, see, from D part it is given that if St is non-singular, then T is 1 1 and S is on 2. It is mentioned in our last part. So if St is non-singular, then T is 1 1 and S is on 2. But here dimension of U, V and W are equal. Then if T is 1 1, this implies that T is 1 1, then T is on 2. Why? From this we can write this again. Also S is on 2 and since dimension of V is equal to dimension of W, this implies that S is 1 1 also. So from this we can conclude that if St is non-singular and dimension of U, V and W are equal or finite, equal in the sense having same finite dimension, then we can conclude that S and T are, thus our S and T are non-singular. So I hope you understand all the part of this theorem.